and QCRETE Readymix India Private Limited as a part of technical knowledge sharing. And I'm very happy that QCRETE has been doing this wonderful job. And today it is the 72, that is QCRETE webinar series number 72. And today we have one of the important topic, and even we have one of the for all of us, we have been waiting to listen to today's speaker, Engineer Juan M. Pereira. Sir, am I pronouncing it right?
It's difficult for you. It's Juan Manuel, but you can call me JM. That's fine.
Okay, JM. Yes, sir.
JM.
Kindly excuse. Okay, and we have been, on the job of mitigating the technical informations, latest updates in the field of concrete technology and allied things from different resource persons, and the introduction part and other formal things will be done by Kaushika sir. And prior to that, I would like to tell that kindly switch off your mobile phone, number one, or put it in silent mode. And second is kindly turn off the video, that is the camera part, so that the bandwidth, internet bandwidth is fully utilized for the this particular webinar. And also request kindly mute the mic so that no disturbances are become being a part of this concentration kind of a talk. We don't want to listen to all those things. So without wasting time, at this moment I would like to recognize the presence of Vice President South, Dr. Nagendra, in this, that is from ICI. Dr. Nagendra, welcome you, sir, for being part of this talk. And there are many important attendees and participants among the this webinar. And without wasting time, I hand over the proceedings to Engineer Kaushika to take it further. Thank you so much, sir.
You're muted.
Kaushika ji, mic.
Good evening to all.
Yeah.
I formally welcome Juan M. Pereira for this webinar, and I express my sincere gratitude to him, and also to equally to our Mr. Suresh Tripathi, who is our friend and associate, who has been instrumental in bringing Mr. Juan Manuel Pereira for this webinar. We are thankful to you, Mr. Pereira, sir. I'll just introduce him. The biodata is like a booklet, but I will just read the salient points from this. Mr. Juan M. Pereira has a master's degree in materials engineering from University Madrid, and he has done BSc in engineering, Universidad Austral, specialization industrial organization 2002, and presently he is working as CEO. Very interesting name, Concrete Watcher SL Spain, very beautiful name. And this company is a startup company based on his own patent for monitoring system based on computer vision and AI analysis, and combined with concrete quality software he has made. It can also predict strength and durability of concrete before pouring it on site. Currently, he is also managing director, Concrete Quality SLU Spain. It is a self-owned company designing and commercializing software and monitoring systems for digitizing the construction industry, targeted at all parties involved with concrete mix design, production, distribution, phasing, and quality control. You can find more information of this software on www.concrete-quality.com. It has a lot of features and benefits for the users. And he's also currently Director Technology and Materials, OSA Sustainable Architectural Engineering, which is operating in Spain and China. He has patents in artificial intelligence system for in-transit concrete monitoring. He has also a patent system for monitoring durability and service life production, CDM, for concrete elements with embedded sensors. He has worked in Emirates, Saudi Arabia, to an international company producing microsil, a pozzolanic addition to improve durability of concrete mixes of all kinds, solving durability issues to comply with especially RCPT values. And he has worked extensively and monitored the project, Fast Track Metro Project, Riyadh, Saudi Arabia. He is full member of MICT, Institute of Concrete Technology, UK, 2016 to present. Earlier to this, he worked as quality manager, Prensa, Precast, Saudi Arabia, 2011-12. And he also worked as technical department manager, concrete admixtures, MOPE, Spain, 2008 to 2011. He also worked between 2005 to 2008 in QCRETE, Spain, technical assistant. He worked as a plant manager, QCRETE Readymix, Spain, 2003 to 2005. He has given many lectures. Some of them are plenary speaker at the International Concrete Technology Forum, Dubai, 2024. Keynote speaker, 5th Concrete Industry 50 seminar online. Expert speaker in 2022 at Innovative Concrete Design and Application Summit in Berlin. So the list is very big. So I will stop at this, and once again thank him for accepting our invitation. Once again, I thank our Mr. Suresh Tripathi for bringing him here. We are thankful and grateful to you, sir. And the floor is now open to you, sir. Thank you.
Okay, well, thank you for the introduction. Thank you for the opportunity to speak to you, all of you today. I really appreciate that, and especially Suresh that made this happen. So I'm going to start very quickly with an overview of what you just presented about the systems and the technologies we have, okay, to give you a brief overview of them, different technologies. So I'll be sharing my screen, and please stop me if you don't see it, okay? Okay. Okay. So these are the technology we developed. This concrete quality software for quality control, mix design optimization, concrete watcher to monitor the trucks with AI, and concrete life prediction, which is the system we are speaking more of today. Okay, so all of these they work as independent systems. Okay, of course they can work together, and they cover the whole life cycle of concrete. And I'm going to jump to this one here. If we have the whole life cycle of the material, starting with the raw materials, then designing the mixes, we can use the concrete quality software to register all the information about raw materials, the mix designs, the production the transport, the performance on site, meaning the test specimens and the slump and all these tests. Okay. This system that we're speaking today is to characterize durability, okay, and that relates to designing the mix, and that relates also to monitoring on site. Okay, so that's why you see it in different stages. Also, we have concrete watcher to control the transport. So all in all, we have different technologies that cover the whole life cycle of the concrete. Is the closest thing you can get of the digital twin of the material concrete, and this can be integrated into BIM models and all of that. Okay, so in the end, as a producer or as a consumer of concrete, these systems, they give you a total guarantee, okay, and total traceability with this know your concrete concept, you know, to know what's really happening at all stages. Okay, that's why we based our technologies in monitoring new things that have not been monitored so far until now, and also with artificial intelligence to make sense of all this data and to optimize the procedures. Okay, so you have this guarantee for the material through the whole life cycle, and also towards the circular economy and reducing the carbon footprint of concrete, introducing new materials, etc., etc. Okay, so this is a brief introduction. So I'm going to jump to the presentation of the concrete life prediction system. Okay, I'll go quick through this one. It's a bit long. Because I want to show you also some real examples of applications and to show you the latest improvements we've done with the software towards modeling and towards simulating and predicting the service life. Okay, so durability is a very big concern worldwide. It has taken more importance recently. Okay, this is a quite recent thing, or a recent collapse of a total collapse of a bridge in Italy. So this is a first world country. This is not 10 years old. Okay, so these things happen every day. So it's really important, and the standards and all the world has been moving towards this concern about durability, how to design, how to test it, how to guarantee the durability of concrete. Okay, and this relates to safety. This relates to sustainability, operational costs, etc., etc. Okay, so usually we design with a service life target. Okay, let's say 100 years in this example. So whenever these the structure doesn't reach that, there is a cost increase in the safety risk. Okay, these are some statistics about bridges, which is one of the most analyzed structures because of the consequences of the collapse. So a lot of these bridges, both in the USA, in Europe, in China, they are structurally deficient or in danger. Okay, and these countries we have good statistics about. I'm sure you know how the state of the structure is in your region. Okay, so good and bad examples of service life. This is a Roman bridge. Of course, this has no reinforcement, so that's an advantage towards the durability, but this is something that's well designed, even without reinforcement. You know, this is almost 2,000 years old, and cars go through it daily. Okay, and this is the bridge we've seen before that lasted 50 years, basically. Okay, so as I said, the international standards are moving towards this goal of durability. Okay, detaching the strength from the durability, because we all know that it's not, there is a relationship, but it is not a constant relationship through all the mixed designs and through all the different binders. Okay. So there was the initial reference of this was the ASTM standards for non-destructive electrical resistivity testing. Now there's part, of course, an European standard on that, and this is what we base our system on. Okay, the non-destructive test, which is electrical resistivity. Okay? And the important thing is that we do monitoring because monitoring is much more representative than cubes or cylinders or samples that you can take on site. Then you cure in the lab. So they are cured in the lab conditions. It's not real site conditions. There's also the chain of custody of this, how the concrete was sampled, how it was cured, how it was transported, tested, etc., etc. Okay. So we consider that monitoring is much more representative of the real concrete in the real structure, in the real conditions. Okay, again, this know your concrete concept. So basically what this slide says here. So what we built is a patented innovation, the world's first innovation, okay, which is the service life prediction with these embedded sensors for electrical resistivity. We did not invent the sensor, okay? We made the system as, we took existing technology and proven designs of these sensors, and we made it into this comprehensive system to predict the service life. Not only measure, but also do this prediction. And this is a key thing in this to guarantee 100, 150 years of service life. That is what most new designs are talking about. Okay, so within this whole ecosystem of SHM technologies, structural monitoring, structural health monitoring technologies, there are environmental, of course. You have like a weather station that you put on your structure, usually a bridge. Okay, so you measure temperature, moisture, wind, etc., etc. There are a lot of physical sensors. Okay, and I take the example of bridges. It's not only for that, but it's a very good example for vibrations, displacement, strain, different load sensors, etc. And there also are these technologies that measure the corrosion potential, etc., but they are measuring the steel. Ours is for the concrete, okay? What we measure, what we correlate to with this non-destructive electrical resistivity method is to the porosity of the concrete, okay? So porosity has an impact on everything because it tells you, it shows you how the concrete is evolving. So it relates to strength, it relates to chloride permeability or carbonation, okay? Also the maturity of concrete. And it can also be related to these type of damages that happen later. For instance, alkali silica reactivity, which starts with micro cracking the concrete from the inside, also delayed 8-inch formation, DEF. So any of these expansive things, expansive damages, they increase the porosity because they form micro cracks. So we can detect both how the concrete improves over time and if these things happen, okay? And it's, like I said, a non-destructive test, so we can measure this continuously. That's why it's a monitoring system, okay? So the monitoring system is pretty straightforward. It's a unit, okay? This is the sensor that goes embedded. You see it has 4 electrodes. This is called a Venner probe, the design of this sensor, okay? This is the bit that goes embedded in the concrete. This is usually like 7 centimeters long, like my finger, okay? And this is the transmitter that logs the data, transmit that to the cloud, to the application, etc., etc. Okay, and this stays outside of the concrete. So it's basically installing this. I will show you some examples, some pictures. Pour the concrete, and that's it. Okay, this was initially designed for new construction, so to pour the fresh concrete. But later we developed methods to include these sensors into existing structure to make an assessment of the structure, the conditions of the structure now, and then with the sensor make the predictions of what is the remaining service life of existing structures. So there's also that. Okay. Of course, this goes with the monitoring plan. Okay, we help with that. We're not a sensor factory, and we sell a lot. This comes with consulting involved because where you put your sensors, what is the most optimal position, how many you need, okay, to optimize the number of sensors, what are you looking for into that position, okay? So there is some engineering involved, and then there's support for that, okay? So we have a comprehensive solutions where we have the sensors, the data logger, okay, the transmitter, the special software, and the consulting support with our some public and some proprietary service life prediction methods, and I will show you in a moment, okay? So this applies to basically everything, both producers of concrete, okay, which can be in the design stage with laboratories, okay, characterization of mixes at ready-mix or precast factories. Okay, and then the users, public works is the most prominent, of course, with more critical structures, more budget for monitoring, or even including the monitoring plans and these monitoring technologies into the projects. Okay, so they are mandatory, and this is coming from the owners, okay, or the designers of the project, because they need to guarantee that durability, okay, that service life. But also in other types of construction, residential, logistic, industrial. Okay, so this is applicable to any concrete structure. Okay, this starts at the project stage. Okay, where there are some durability specifications. So the engineers and engineering firms, they have these durability requirements. They specify what type of monitoring needs to be done. Okay, and also the mix designs, how long the service life needs to be. So the design stage, there is the material selection, okay, which materials we can use, which perform better. Okay, this system gives much better information about that. And that's an advantage because this is not a lab test. This is something that you can use in a lab, okay, to simplify and streamline your processes in the lab, because instead of curing a sample and then taking it out and conditioning it and then testing it with the lab equipment that usually takes at least a day. You know, I'm thinking chlorides like the RCP. It's like a one test per day per unit you have. This is continuous monitoring. So once you have your test specimens, just let it sit there and you get data every day. Okay. So that helps with this selection and design, selection material design of the mixes. Okay. And it's the same system that you can apply at the construction stage. Okay, so the same readings you get in the lab or the design is what you get in the construction. So this is really important to check the quality of the construction process. Okay, because we can design the best mix, but then what happens during transport? What happens during the pour? What happens in curing? Okay, anything that we do poorly will degrade the quality of that concrete. Okay, so we design for one quality and one service life, but then we get something different. With this system, you can measure the same that you design in the construction. Okay? And then in the operation, so long term, this is for the owners of the structures, of the operators of the structure. There is the guarantee that you have a durable structure, that you have continuous information. You see the evolution of the concrete over time. So you can plan your maintenance. You can detect if there's any sometimes of internal damage. This also involves reducing the premiums of the insurance. Okay, so the insurance cost is lower, the maintenance cost is lower. So it has a lot of impact through the whole process. Okay. So basically, this a summary of what I told: the characterization, mix optimization with the producers and the designers, okay, of the concrete, and for the engineering and the construction companies and the owners, concessionaries of these structures, there is also added advantages of this. Okay? So these are some of the people we work with, okay, both domestically here in Spain and internationally. Okay, so what we do is we have with maturity, the key of maturity monitoring is this initial stage is 0 to 3 days. Okay. You can go up to 28 days for strength monitoring, okay? And then we have other monitoring technologies that they detect the corrosion or they detect maybe some chloride ingress. So what we cover is this gap, okay, in between, because we are measuring continuously and we can do this service life prediction, okay? So we include this data and combine with this data, okay, which is an added value, okay? So we can prevent or foresee the corrosion before it happens. So we can, like I said, it's applicable to all players in the industry because we can design concrete with service life targets. Okay, we can design concrete for durability. Okay, so that's an important step towards guaranteeing that the specifications of the projects will be met. We can also see and correlate this with compressive strength in real time. And the importance of this is that it complements these maturity systems very well, okay? Because once the maturity method or methodology. It's not it's a limitation of the method, not that each particular sensor. Okay. Once it stops working, because at some point the temperature differences they don't correlate to the strength. Okay. We've seen that the resistivity, electrical resistivity, it does keep that correlation. Okay. So we can monitor the strength for higher ages, not just the initial stage. Okay. Of course, and this is something we've done a couple of years ago. This is the resistivity for different concrete types. Okay, so it can vary very, very much. Okay, and these are the compressive strengths. So each concrete mix, each cement type, we have its own correlation, but it can be easily established. Okay, and once it's established, it correlates very, very well. Okay. Regarding sustainability, okay, we all know this KPI, which is the amount of CO2, maybe kilograms, maybe tons of CO2 per cubic meter, okay, or per ton of concrete, depending on what unit you use. And we make a case that this is not a good indicator, okay, because we can have, and this is a very simplified example with raw numbers, okay, but this is realistic. You can have two concrete mixes, okay, with different cement types, imagine, and one has a lower CO2 footprint per cubic meter than the other, okay? So if you need to make a decision about which concrete is more sustainable, of course, everybody will go for the lowest one, okay? But what we do is we combine with the service life prediction. Service life prediction is years until the corrosion starts, okay? So it gives you a time span in years, which is very easy to assess, towards the durability and how many years that structure will be in service. So if we put that into perspective and we say that the lowest CO2 has 20 years of service life and the one with a little bit more has 30 years of service life, we have a much better indicator, which is the yearly CO2 footprint of each concrete, okay? Because sustainability can only be, we can only think right about sustainability if we think it long-term, okay? And I know that sometimes the requirements are simplistic, so they ask for the current CO2 footprint, okay? So they don't take into account this, but they don't take into account these things because they were very difficult to measure, okay? And as usual, the technology goes ahead of the legal part, okay, or the standards. So this is something that as technicians, okay, we push for, okay, because making a better assessment for sustainability of how sustainable the concrete is, this benefits all of us and the future generations everywhere, okay? So this adds this by ear, okay? So it's a much better indicator in a very, very simple manner, okay? I will skip a little bit ahead of this part because I want to show you the references, but this can be used strategically for new type of blenders to validate the admixtures that, for instance, extend the service life or the reduce the porosity. It is an actual way of measuring and proving that this works, okay? So this is interesting for many different players, okay? So it's a practical and effective solution, okay? Just a recap, we make the service life prediction, we can measure chloride permeability, also we have carbonation models, okay? We get weather information automatically, okay? The sensors, they connect automatically to a gateway or a router, okay? So all the information, you don't need to go and download anything from the sensor, it's all sent to the cloud automatically, okay? And this links to of course, our concrete quality software, where you can get all the traceability of the materials used, all the trials you've done and all the design, all the quality certificates, all the tests that you do during construction, etc., okay? And then we can even connect to the plant and get all the loads for everything. So you have a comprehensive set of information. And this is not minor because I've talked to many people around the world, and when something happens, okay, there is a problem and you need to investigate, it's very hard to put all the information together, okay? Because you can have the batch information in the batching system that maybe the plant is no longer using. Maybe you have some Excel files for the test, some PDF here, something there. So putting all of that together is really, really, really complicated. Okay, sometimes parts are missing. In this case, we put everything in one platform, in one format. Everything is perfectly traceable. So this adds a lot of value, and it's a very handy tool for the producers and the designers. Okay. So there is this about the international standards. Okay, there is, like I said before, more and more inclination of the standards towards addressing the durability. Okay, and so this is the European standards. It's an abstract. Okay, these are the it's an annex that will be added to this standard, which is the electrical resistivity standard. Okay, this is approved. It's only pending publication. This standard has two methods. One, the volumetric resistivity, okay, which is the reference method. Another one is the surface resistivity, which has been there for many years. And now the EN standards approved this our system basically because we have the patent on it. To be incorporated as one of the methodologies to assess the electrical resistivity of concrete with the embedded sensors. Okay, so pending publication is already approved. This will be standardized in the European norms. Okay, so this is an important reference for the system and for the use and approval of the system in real projects. Okay, these are also some technical recommendations in the ALCOMPAT is the Latin American Laboratories Association. Okay, they don't have a Latin American standard, but they have this reference or guidelines. Okay, this is there incorporated as well. Okay, so and I'm going to speak about this at Federación Internacional du Béton, the International Federation of Concrete, FIB. Okay, because we use these methods, they're models for prediction of durability, but this is incorporation of standards or how this relates to the standards. I'm going to skip ahead because this is quite dense. Okay. Of course, this is patented. We have the patent granted a few years ago. Okay, we had a European Seal of Excellency with this project, but in 2020. Okay, so we had some funding to develop this project from the European Commission. Okay. And we got this through the Madrid community in Spain, okay, in 2023. So this is a very quick overview of the system of the presentation, okay? So I'm going to jump to a few references, and then I want to show you the software working with one real case, okay, that we've been monitoring for almost 3 years. And then we're going to go to the questions part, okay? So some references, so you see different applications. This is the unit, okay? This is something you can hold in your hand. Like I said, the sensor is quite small in footprint, okay? We can design them differently for larger aggregate sizes, these electrodes are separated more, okay? This is 15 millimeters, this is a temperature sensor. So we measure the electrical resistivity and the temperature, which are very closely correlated because the more the temperature rises, the lower the resistivity is because the ions can move more freely. Okay, so we measure both. Again, some people that we work with, these are some initial calibrations. Some of you may be acquainted with Dr. Carmen Andrade. She was a scientific advisor for the development of all of this. So this is her, and we were working with Holcim, and these were the tests we ran for the European standardization, this standard I showed you before, okay? This is with new types of cement. You see this black test specimen. This is not coloring. This is a high ferrous binder, okay? So we're comparing the OPC with this binder and how it performs, and this is in Belgium. This is MAPE in Spain, okay, with for admixtures, application of different types of admixtures to increase the durability of concrete, okay, or reduce the carbon footprint of concrete, and how that relates to the durability. Acciona, this is a construction company in Spain. We made this project in the port in the north of Spain, a city called Gijón. And this is the one I'm going to show you. We cast different types of concrete with different exposures. In this case, and I'm going to enlarge this one so you can see it better. Okay. So it's these elements, okay, that they are all painted with epoxy on all faces except the one exposed to the concrete, simulating a real element, okay, exposed to like this pier here. And one remains in the splash zone, one remains in the tidal, one remains submerged permanently, okay? And there is another one 100 meters from the coast. This is a two-stage project. We did 3 types of concrete on the stage 1, another 3, so it's 6 of these in total, okay? And this is the one I'm going to show you in the software. So this is a very interesting project because we tested many different types of concrete. The durable ones, the ones we knew they were not durable, ultra high performance concrete, very comprehensive. And this is a company that has international reach, okay, a Spanish company with international reach. This is precast. This is the largest precast manufacturer in Spain, okay. You see here how we tie the sensor. Sorry, let me pull this up. Okay, so how we tie the sensor to, in this case, it's not a rebar, it's a pre-stressed, okay, tendon. So to measure, because this is the most critical part, okay, for durability. So we measure the cover here, and we see how the chlorides or carbonation ingresses to the passivate this element, which is critical because this is pre-stressed. Okay, so this can be applied also in the factories. Okay, this is with Saint-Gobain, again with admixtures, a different set of admixtures. This is all that we work with the University of Porto in Portugal for this process or procedure to introduce the sensors and how to assess an existing structure, and what is the procedure to put the sensors inside and make measurements and predictions of service life of existing structure. This was a project with the University of Porto, part of that big European funded project. Okay, so we have a whole analysis on this and some AI models as well for this. Okay, a lot of lab tests, a lot of here you see a lot of lab tests for carbonation, for chlorides, etc., etc. Then some real structures. This in Porto, you see the cruise ship there. This is a structure like a test structure we have in close to seawater, so this ambient for sea mist, okay, and how it works. And you can really tell when the moisture goes up, when it's raining, it's not raining, how it impacts the mobility of these chloride ions inside the concrete. Okay. This is a nice project, again, with the Port Authority in Bilbao, a different city. And this is with recycled aggregates. We did a 400 square meter test for a slab in the port with different types of replacement of recycled aggregates. So one panel is normal concrete, another one is a 20% replacement of the coarse aggregate with recycled aggregates, and the other two, they had a higher proportion of recycled aggregates, even going to 100% of the coarse and 25% of the sand with recycled sand, okay, which is a very big step up towards reducing the carbon footprint. Also, with new wonders, with high replacement of the clinker with supplementary cementitious materials. And the port is really interested in these things because when they demolish a structure, they need to know if they can recycle it or not and how that affects that. And especially in ports, having 100% uptime is really important. And these are other types of investigation with universities in Spain and different companies, okay, experts in slabs, for instance, and polished floors, like an Amazon warehouse, okay, for logistics. Okay, so we did a lot of tests with this. Okay, this is with the cement manufacturer for exposure to seawater, different experiences as well. A very big set of, this is just, a tiny bit, okay? We cast over 100 test specimens, okay, with different types of blends of cement. Okay. Also in Australia, we have some references, some other references worldwide. Okay, this is a mixture supplier. This is a consultant in the Middle East. This is a consultancy also in the UK. Okay. So there are many different types of uses, different experiences through these years, and I'm going to show you the software. Okay, the latest developments of the software. Okay. So here, okay, and this is one of these port structures you've seen, these blocks. This is the one that is one of them is in the with Centre. This is a blend with GGBS. Okay, like maybe 40% replacement of the clinker with GGBS, and exposure class, the most demanding, which is the tidal. Okay, because it dries and wets. Okay, so what we see here is almost 1,000 days of readings, which you can see here in this graph. Okay, we have weather information, we have moisture. This is a very moist area. Okay, the city itself is very moist. We have ambient temperature. Okay, we gather all the weather information as well. If it's raining, if it's sunny, the wind, etc., etc. Okay, and what you see here is the pink outline is the ambient temperature, max and min. This here is the temperature of concrete, and this is the electrical resistivity. So you see this effect that when the temperature goes down in the winter, electrical resistivity goes up, meaning that it's harder for the chloride ions to move through the concrete. Okay, this is the same for carbonation in a carbonated exposure. Then in the summer it goes up, so concrete goes down, but it has this trend. Okay, we can also derive RCPT directly. Okay, because there's a direct correlation between electrical resistivity and the rapid permeability, because it's an electrical test that you measure the charge transmitted through the concrete. So the electrical resistivity is part of that. It's basically applying Ohm's law kind of directly. Okay, and of course the software allows you to see all the readings and export the data, etc., etc. Okay, and then what we do is a lot of analysis, and we get a lot of information out of this data. Okay, so it starts with these two parameters. The activation energy is a parameter that tells you how much the resistivity changes with the temperature change. Okay, and there's a lot of complex mathematics to remove the effects of drying and wetting and the moisture, etc., etc. So basically what we get is that this is a yellow, the temperature. You see in gray the readings, okay, uncorrected. And what we get with this correction, okay, is that this blue series, which you see that is like linearly improving, okay. And this is important because this allows us to correlate a reading we have in a real structure to what we would be reading in a laboratory environment, okay, because we correct this as if it was 20 degrees as in a laboratory. Okay, so this will allow us later, I will tell you in a moment, to use any type of test that you do in the lab, whether RCPT, chloride diffusion test, whether normal or accelerated, etc., etc., to correlate that to what we measure with the resistivity. Okay, but let me go to that part. Okay, then we have the aging factor. Okay, the aging factor is one of the critical parameters that all of the durability models use to predict how the concrete will evolve over time. This is usually tabulated. Okay, so it's known that for different cement types, for instance, for this cement type, the typical value is 0.6. Okay, ranging from 0.5 to 0.7. We actually measure this in our concrete in this exposure, and it's almost 0.7. So, and this is an exponent. I will show you the equations later. So this small change from 0.6 to almost 0.7 has a huge impact on the prediction. Okay, so you see that there is a very good fit, and we're showing it here as a logarithmic axis. So these blue are the readings, okay, corrected for that temperature, okay, and as we did in the previous step, and this is the aging law. So the slope of this curve is that aging coefficient. So it tells you how much the concrete will improve over time. So we read, and when we have the readings, we use the readings. When we don't have the readings yet, because we are predicting for 100 years, we use this, and this is fitted to the real concrete in the real structure, not something tabulated. Okay, so it gives you a much better and much precise prediction. Okay, and this is a key point in doing this monitoring. This calibration is, and this is an example, if I have one chloride migration test at 28 days with this result, okay, and we can add as many as we need, okay, if we have, for instance, 90 days, 180 days, whatever, we can add all of them, and the system will automatically make the best fit through all of these points. So basically what we do, we have the shape of the curve with this aging factor, and here we have the level. So with these two things and with the activation energy, what we can do is transform this reading of electrical resistivity into whatever unit, whatever type of measurement you're doing in your lab. Okay, if this is RCP, we can transform this reading into a RCT, real time. If this is chloride diffusion coefficient, we can transform this into diffusion coefficient, real time. And you can use that in the models, and this is what we do. Okay, so any test, even with one test that you have, everything else works. Okay, so we have these basic models. These basic models are the models from Dr. Carmen Sandrade's investigation back in the 90s, when she designed, basically she put all the theory together for the RCP test. That's the basis of the RCP test, is her theory. So we have these two models. There is a very basic model, a simplified model with no aging, meaning that we don't count this aging factor. And this is based on the 28 days result. Okay, so if the concrete stopped at this moment and you expose it like that, how many years it will last? That marks the bare minimum, okay, of the service life. So in this case, it's 50 years. This is a 100-year concrete. So the bare minimum at 28 days, okay, is 50 years in this case. So this is a very good concrete. With the advanced model that takes into account this measured aging factor, and we put it here, you can put the manual entry or the tabulated one, we calculate that it's almost 300 years. Okay, so this is shown here. This is one that's stable with no evolution. This is the prediction, okay, the brown one, and this is the actual readings. Okay, so we see that it fits quite well. Okay, then we have the fit model. Okay, the fit model is this one I have here in this presentation. I'm not going to go too deep into the equations, but it's worth telling you this bit. Okay, showing you what the equation is like. So this is the model, and this is probably the most well-recognized model in the world we have for chloride ingress. Okay, so this is initiation model. So how much time it will take, okay, until the chlorides reach the threshold concentration for the corrosion to start. And then there is a velocity or speed of corrosion that we can also calculate. But this model is telling us what? It's telling us the concentration, C, of the chlorides at X, the depth, how deep inside of the concrete, at the time T, okay, at any time. So we have the initial concentration, this is an effect of wetting and drying, and this function, okay, which is, it's called the error function complementary. It's a weird name because it's misleading. It's basically the entails of the Gaussian function, you know, the normal, the bell curve, okay, that gives you how much the ends are, because it's the complement. You can also do the center. And this correlates to this thing. This thing is the apparent chloride diffusion, okay, coefficient. And this is something that depends on the weather with this K, and depends on changes on time, and changes with this alpha, which is the aging exponent, that thing we calculated before, okay? Most people use this model as a deterministic model, okay, which is not what the FIB intended. Each of these parameters, they have a distribution of probabilities with the standard deviation, et cetera, okay? So you should do a probabilistic modeling on this, okay? So the advantage of what we do is that all of these things that are probabilistic, like the alpha is probabilistic here, this K is probabilistic, we actually measure. So we replace all these probabilistic things with actual measurements. Okay, so that reduces the risk, or the that increases the trustworthiness of the prediction much more. Okay, because you are like removing variables. Okay, because we are replacing these distribution probabilities with an actual thing. Okay, and this shows in the software like this. We have this all the configuration here. Okay, so if this is a concrete, okay, and this is green because it's like the initial concentration of chlorides, okay, and this is the river. So if we play, we can make like an animation, which is what happens over time, and you see how the chlorides will be more and more concentrated over time, how the concentration is distributed, how this front, which is the critical concentration for the corrosion to start, will move over time. Okay, and when it reaches this river, okay, it will turn from passive to depassivated. I will speed this up. Okay, so you can see all the progression of how the concretes will, how the chlorides will be concentrated inside of your concrete. Okay, this is another representation where your concentration profile. Okay, and this is the critical one. So when this one reaches here, that's your end of life. Okay, so this is the FFB model, and then we have our own proprietary models. Okay, so in our proprietary models, what we do is basically take all these equations, okay, from FFB or from these basic models, and we put the real data in. Okay, and that changes the prediction. Especially, I think that this is the best one, okay, because it gives you a much more realistic service life prediction. Okay, and it's also based on real data, and this prediction will keep improving over time as we get more and more readings. This prediction will keep improving. Okay, because it will be more and more realistic, because more time passes, all the coefficients are more accurate. Okay, and then making sense of all of this. Again, this is also moving, so you have these thresholds, etc. Okay, so this is very complex. It has a lot of different things and different concepts to convey. So we added an AI analysis. So this is an AI with trained with all this information and knowing all this theory. So it helps you analyze all of these results. Okay, so in summary, we have these different methods that give you different service life expectancies. Okay, so the AI understands which one is better, which one is worse in this which situation. It can compare all of them. It can give you recommendations and predictions. For instance, this is here saying, okay, this is a good concrete because this coefficient is quite high. This activation energy is outside the normalized standard, so you need to keep working on it, keep measuring it. Okay, it gives you how much of the cover is consumed today. Okay, so this is a real indicator of that you can test. You can go and take a core drill of your structure now and see if this matches. Okay, and the prediction. If it doesn't, you can input that result as well and, let's say, readjust the prediction. So in the end, it will give you a conclusion. In this case, the passivation is not expected, so that it will meet the 100-year design life. It has a moderate confidence here because it has only one test for the chloride diffusion, so it recommends that you have more, and it gives you here the recommendations. Okay, so it's a very comprehensive system, and you don't have to be a complete expert in this to understand, because the AI will analyze and explain everything to you. Okay, so this is really valuable to interpret the results. Okay. Okay, so I think we are kind of good on time still. Actually, time passed, but I met my 45-minute target. One more thing I want to show you before I go to the questions is this, because I want to make this very clear, and it's this diagram here. Okay, so what this represents. Okay, each of these cubes here is actually a cube or a cylinder. Okay, that you cast of concrete. So when you're doing a mix design, okay, or characterizing a mix or a new material or something, something new in a mixture, you do laboratory tests. Okay, so you do your mix, you make your mix design, and you cure it for 28 days, 90 days, 180, depending on what your plan is. Okay, usually these chloride migration or carbonation rates, they are accelerated tests that work well at 90 days. Okay, and non-accelerated tests that are a bit more trustworthy, that you need to wait for 180, 360, or so, half a year, 1 year, even 2 years. Okay, so doing this type of tests is okay for design, but a 2-year-long test is not at all okay for control of the site. Okay, you cannot take a sample and let's see how this works in 2 years, because in 2 years maybe the building is finished. Okay, so our approach here is to take the resistivity sensors, okay, these are our sensors, and just when you do any testing plan, you just cast 2 additional ones for each concrete. So you have test specimen for strength and for chloride migration and for carbonation, whatever. So you cast 2 more, and these give you continuous measurements, so you can keep reading up to any age, okay? And these readings will correlate to the strength, to the chloride migration, to the carbonation, to anything you measure, okay? Just by adding 2 additional test specimens and leaving them there in a corner, in a tank, reading, reading, reading. You don't need to interact with them. It's just continuous. So, and this continuous information, in my experience, gives you a lot of new perspectives, because when we see 1 point here and 1 point here in the chart, you know, like 28, 90 days, in our mind, this is a straight line, you know. But you see how these things evolve over time. It's not straight, or maybe it's going up, or maybe you get surprised that after a year or 2, things that you didn't expect to keep evolving, they do keep evolving, okay? So it's very interesting to have this continuous measurement, and especially now in the age of AI, having new data and having more data, it's a critical advantage, okay? Because we all have the same AIs, okay? We can train our own, we can tailor it a little bit, but these systems, they need data, okay? So whoever starts getting this data now, okay, in 1 year, in 2 years, in 3 years, when everybody has the most, or a very, very intelligent AI and it solves everything, it knows everything, the advantage will be these 3 to 5 years of data, okay? That is the real advantage, a competitive advantage, to have more data than the others, because the AI can analyze, but it cannot make the data up, okay? Because that's where it goes wrong, when it invents things that are not true. But if you have this truth and you have these records, okay, they will become more and more valuable over time. Okay, so I'm finishing with this, and let's do a few minutes of Q&A. Okay.
Andakumar, can you
Yes,
take
sir.
up
Yes, sir.
questions?
Yes,
Some
sir.
questions, whatever has been.
Yeah. Good evening, everyone. First of all, I would like to warmly welcome and thank you, our respected speaker, for the taking our time with us today and for sharing the valuable knowledge and experience with us. You can ask your questions in your QA box, and I'll shoot the question with the speaker. In the meantime, sir, we have few questions from the attendees. I'll putting those questions forward on their behalf.
Okay.
So
I'll go
first,
to, okay.
First question from Ma'am Anjali Matthew, ma'am. The question was, when we have your device embedded in the concrete, we can get durability factors from how many years, for how many years, also till how many years we can get that information.
Okay. Yeah, the system is designed to be permanently installed. Okay. For instance, when we start getting all these coefficients like aging factors and activation energy and all these things that we feed them to the models to do the predictions, there are some things that you need to wait until 28 days passes or 90 days passes, and the more you have, the more precise that will become. Okay, so the system is designed for that, to be long-term monitoring in the structure, and also if there is any risk of any expansive damage to the concrete, maybe alkali-silica reaction or delayed ettringite formation, this sensor will be able to detect that, because this microcracking, will suddenly start increasing the porosity, so it shows us as a decrease in the resistivity. So if you keep monitoring, and this happens 8 years from now, if you are monitoring in year 8, you will see that in the data. Okay, the system can produce an alert on that, because this should be going up or being stable, maybe with these seasonal changes, but then it starts going down. So before you see it outside, and the damage is irreversible, maybe you can take some action because you have an early warning. When does it happen? We don't know. Maybe 8 years, 10 years, 15 years. Okay, the system is designed to be there for all that time. Also, this is interesting in combination with, for instance, active corrosion systems, preventing systems, like these sacrifice electrodes that you need to activate. Okay, so if you make a structure and it's critical structure and you put these systems in place, when do you activate this protection? Okay, because if you activate it now, this lasts for 15 years. So you're protecting the first 15 years, maybe it's nothing inside. Okay, so when you really need them, you don't have them. If you can do this prediction, you can plan for when to activate these systems, so you can optimize that and also reduce or delay your maintenance on the structure. So basically, you can read it. You can keep them reading all the time you want, and the more you have them, the more advantageous it becomes.
Thank you.
Okay,
Thank you for the answer, sir. And another question from Gopal Reddy, sir. There are other In-Situ monitoring. There are other testers or In-Situ monitoring the concrete strength, etc. So extras, etc. are there. What is the unique and differentiating features of this device you have invented, sir?
Okay. Yeah, this is complementary to many other monitoring systems. Okay, this is not really to replace anything else, but to give you complementary information. What's quite unique is that we measure the electrical resistivity, so that relates to the porosity, and we do the service life prediction. That's the unique thing, and that's what we have the patent on, that we are able to measure something inside of a concrete and make a prediction of service life or durability for that. The other sensor systems that are available, okay, most of them are for physical properties. Some of them are for chemical ingress. There are some like chloride chemical ingress sensors that you put at different levels, and they tell you when the chlorides reach a certain concentration at a certain level. And these are complementary because you do a prediction with ours, and you can verify the prediction with other things. Okay, instead of taking a core drill every 5 years and making these chloride profiles, okay, you can have a monitoring system, and that's compatible. Okay, it's not one replacing the other. And actually, if you have both, you have much better predictions and much better maintenance plans and much better asset management in general.
Thank you, sir. And another question from Mr. Kritik Hegde, sir. Is there any limitation for the sensor? For example, can it measure only up to a certain distance or cover a specific area?
Yeah, the sensors are, they measure inside a limited area that's defined by the size of the probe. Okay, the standard is designed with 15 millimeters separation of the electrodes. Okay, that is for all the concretes for aggregates up to 20-25 millimeters works well. If your concrete has a larger aggregate, okay, there are options for larger probes. The larger the probe is, the more area it sees. Okay, and also the sensor is directional, meaning that if you put the electrodes facing the cover, they will read the properties of the cover. If you put them to the inside, to the core, they will read the properties of the core. And sometimes we do that because at one point we want to compare how the cover behaves, how the core behaves. Okay, if there is a big difference between the two, that can indicate that, for example, you have a curing problem. okay? Because if the cover is much more porous than the center, it means that the curing is not correct, okay? So yes, it's a limited area. That's why the monitoring plan, let's say we advise on where to put the sensors, okay? You cannot put the sensors anywhere, that's it. Makes little sense, okay? It's not optimal. So to achieve certain goals and to measure certain things, we need to place the sensors in a correct position, okay?
Okay, okay, sir. Thank you for the answer, sir. And another question from Miss Soumya, ma'am. You have said about service life prediction. So, what are all the factors that software takes to predict service life of concrete, sir?
Okay. Of course, the most important one is the electrical resistivity readings, okay, of the concrete. It takes into account the temperature variations, the weather information, okay, to which this concrete is exposed. Okay, this is automatically recorded, and from that also is the cement type is something you can fit to some models, but since this varies so much, you know, because if you go to a table and it says this type of cement, this coefficient, okay, or maybe between this and that, okay, but is it the low end, is it the high end? The good thing about monitoring is that you remove variables, okay, from all these predictive models. So the type of cement is not really as important here, maybe for some secondary effects, okay, of capturing some ions, etc. Okay, but it's not the most important thing, which is if you don't have the sensor. Okay, also for instance, in the FIB model, there is this weather coefficient, or in the carbonation, there is a weather function. Okay, the weather function is like a prediction of what the weather will be. Okay, this changes, and how good that prediction is. So you have a lot of uncertainties there. What we do is measure that. So all these parameters, okay, we reduce the uncertainty, but basically we are taking into account everything these models take into account, which is the type of cement, the cover you have, okay, that also has a distribution, statistical distribution of the cover. The weather, that's especially important because predicting the weather, it's a very, very hard thing to do, okay? So it gives a lot of uncertainty in these predictions. So we remove that because we are measuring it.
Thank you, sir. Thank you for the wonderful answer. Also, we have another question from Dr. Ravi Kollati, sir. How would you compare the lab test results with the on-site test results obtained using your device? Laboratory samples are tested under the fully controlled condition and cured at a specified temperature. However, the conditions of on-site structures can be quite different and are not always controlled. Does your device or software apply any correction factors to the account for this difference? Also, are there any specific software configurations or setting that should be used when testing on-site structures, sir?
Okay, so it's several parts of the question. Okay, let's take it bit by bit. Comparing the lab with the site, okay? Of course, when you design your concrete, you're in a lab condition, okay? And you're working at a controlled temperature, controlled moisture, etc., etc. But then reality happens on site, okay? This is actually one of these consulting jobs I had in Saudi Arabia, was the seed of this idea, because the problem was that all the lab tests were okay and on-site testing was not. And this was related to this, and how representative a site test is, okay? If you take a sample and you keep it in the lab, or you take a sample and you keep it on site, and how representative that is from the real structure. Okay, so the good thing about this monitoring technology is that you can apply this in the lab, okay? And the software has all the capabilities to say, okay, this is take any reading you have there to lab conditions, okay? So in the lab, it's like you multiply by 1, basically everything, okay? When you go to site, and these are all these things integrated in the software, It takes into account the difference in temperature. You can see if there is any wetting and drying cycles, because you will see this. For instance, it's raining, so you see changes in the resistivity. Also, we get the weather information. So the system has all these configurations to allow you to compare what you are getting in the lab and what you are getting on site. Okay. Depending on the geometry of the element you are measuring on site, you may need to do some geometric adjustment. This is a parameter in the software as well. There is a geometric factor involved, which is quite easy to calculate, okay, or to prove with one single test. But then there are all these configurations that, and I haven't shown you the configuration screen, of course, because it's not the point today. But it can take into account all this information, okay, to make it the most representative, okay, so that you design, when you have a specification, any project gives you a specification for a lab test, okay, RCPT less than 1,000 coulombs or 100 or 200 or whatever, okay. So how do you correlate that with what I'm reading, okay? We all have all this pipeline built into the software, and also we have the predictive modeling based on the real thing, not on the theoretical or the laboratory concrete. Okay, hope this answers your question.
Yes, that was a good explanation. Thank you, sir. Also, we have another question from Mr. Subramani, sir. At what depth from the surface of concrete the sensor are generally embedded?
Okay. Usually we embed them at, for instance, you've seen this picture in the pre-stressed beam. We embed it in the most critical part, okay, with the outermost rebar, because that is the one that will corrode first, okay? So you're measuring the concrete that is protecting that, okay? So it's usually on the outermost rebar with the sensors facing the cover, okay? The electrodes facing the cover, so it reads that. But you can place them in other positions. If you have like a smaller mesh that is not really doing the groundwork of, then you can put it inside, more inside. Actually, you can put them anywhere inside of your structure, even if this is a mass concrete structure like a dam, for instance, because the technology is built in such a way that we can extend the length of the wire of the cable of the sensor to any length, and it doesn't change the signal we read. Actually, in this port structure I showed you, some of the cables were 12 meters long, some 20 meters long, and then we had another 100 meters from the coast. And the readings are the same because the electronic design is made to balance that loss on the wire.
Yes, sir. Yeah, thank you for the answer, sir. We have another question from Dr. Ravi Kollati, sir. What is the cost of this particular device? We are currently using Lumion sensors for maturity and strength monitoring, which are relatively low cost and provide us the both strength and heat of hydration data. Does your device also collect and provide the heat of hydration data, sir?
Mm-hmm. Okay. Yes, we do. We do collect that, but this is not the main goal of our system. Okay, actually, this is a strategic decision of us that we don't compete in that space. Okay, we partner with people local. Okay, for that, because the goal of this system is to assess the durability and to do this long-term monitoring. Regarding the cost, I would say this is, and we can discuss this in private, of course, and it depends on how many you buy, etc., okay? But it's comparable to other systems, okay? And since this is like a specialty monitoring, okay, with long-term monitoring and long-term consequences, the relative cost of this to the value you obtain, okay, is negligible. Okay, it's very, very low because saving a little bit on maintenance, extending a service life of a structure a few years because you do a repair in time, or you do a protection in time, or activating these active corrosion protection systems later, which are really expensive and you cannot, or it's very difficult to install them later, you know, compared to the cost of monitoring, to the cost of these other actions, it's very, very low. It's less than 1%, you know. So it's very convenient. But again, our strategy is not have a million sensors every day, you know, because you consume them very fast. This is a different thing with a different goal. Okay, so that's why even if the costs are comparable, it has a really low impact on the value they provide.
Yes, sir. Thank you. Thank you for the information, sir. Now itself, that's all for the questions, sir, from our end. There is no more questions. Thank you for the answers given by you. Thank you for all the information, sir. Thank you.
Thank you all, and very, very good questions, all of them.
Hello. Hello.
Yes.
We are really thankful to you, sir, for this wonderful lecture on this, I can say, a very new area in concrete technology. And the information given is very interesting. One of the very important things which anybody can identify here is, apart from the technology and the instrument and the device that you have patented, one of the most important things which you pointed out is, let us say, a 200 kg carbon footprint concrete mix having a service life of 20 years, and another one is 240 kgs with a service life of 30 years. And so what do you select? So all this can be monitored properly, and especially what you said is like you can start the protection system or take actions at reasonable intervals based on the information given by this your device. So that will be of great protection and service life, longevity enhancing technology that you have brought. We are really thankful to you for accepting our invitation, and we are enlightened, and I am sure the audience have also gained a lot from your lecture. We are thankful to you, sir. We are really thankful to you, and we are thankful to Mangaluru ICA chapter. We are also thankful to Mr. Suresh Tripathi for bringing you here. Thanks a lot, and thanks for all the audience who have been with us continuously on all our webinars. This is our 72nd webinar. Thank you. Thanks a lot. Once again. Thank you, Anil Baliga and the Mangaluru Centre too, and our other QCRETE team, Mr. Anishka and Nandakumar and team. Thank you.
Thank you, sir. Hi everyone. Could you please register yourself in the QA box? There is a link to get a certificate. So every participants don't forget to register in that link to get your certificate. Thank you.
Thank you, sir. Thank you, Mr. JM, once again, for a wonderful evening.